Okay, going to be working on the homework for 10-7. There's quite a few problems in here, so give me several hours of videos, I'm sure. So number one, I'm doing numbers 1 through 11. So number one, find the domain. So I want to find the domain of the following vector function. R of t equals the vector square root 4 minus t squared, so e to the negative 3t, and natural log of t plus 1. So all we're trying to figure out is what t's I can and cannot plug in to this vector function. I have some issues, square roots. I cannot have a negative number under here, and then natural log, I cannot have a negative I can't have a negative number under here, or in here either. So this argument must be greater than or equal to 0, and this radicand must be greater than or equal to 0. So I'm going to go ahead and look at those two. First of all, 4 minus t squared has to be greater than or equal to 0. That's called a quadratic inequality, and the way that we can solve this is first converting it over to an equation, getting our two solutions, which would be positive and negative 2, plotting those two solutions on a number line, and then just checking some points to see if those satisfy the original inequality. So if I try negative 3, plug negative 3 in here, this will not be true. If I plug a number like 0 in here, 4 is greater than 0, that is true. And then if I plug in something like 3, that won't be true. So I know that everything between negative 2 and 2 will work. So this is interval notation, all x values that are an element of this closed set. Remember, it can be 2, right? If I plug in 2, I get 0, that's okay, square root of 0 is defined. I need to look at this one now. Also keep in mind that I'm not looking at this because e can be raised to anything. Doesn't matter if it's a positive number, could be a negative number, could be 0, it doesn't matter. E is well defined, so no domain issues with the second component function. So on this one, I need t plus 1 to be greater than 0. Strictly greater than 0, right? Can't be equal to 0. So t must be greater than negative 1. That's just a linear inequality. So that means it's negative 1 to infinity. Oh, I put x here. Oops, t. T must be an element. T must be an element of that. So what I'm going to try and find now is the intersection of those two sets. I can do this several ways. I'm just going to draw a number line. The first one says that I have to be between negative 2 and 2, including the endpoints. This one says I must be strictly greater than negative 1. So negative 1 is here. I have to be greater than negative 1, so out there like that. And I cannot be negative 1. So it's wherever these two sets overlap, which would be this region in here. And I would not want to include negative 1, so something like negative 1. And then I would want to include 2, so 2. But I couldn't go past 2. I couldn't go to the left of negative 1 either. So t must be an element of this set. So your domain is that. You could also write t is greater than negative 1, but less than or equal to 2. Yeah, we're done. Okay, I'll let you do number 2 yourself. Number 3, we're going to find a limit. The limit as t goes to 0. Well, you know what, let me do 4. 4 looks more interesting. We're going to try the limit as t goes to 1 here of the vector function t squared minus t over t minus 1, and then square root t plus 8, and then sine pi t over natural log t. So let's see if we have any problems. Let's look at each of the components. As t goes to 1, I get 1 squared minus 1 at 0 over 1 minus 1 at 0. So I get 0 over 0 here. That's a problem. I plug in 1 here. I get 9. Square root of 9 is defined. That's okay. Here, sine of pi. So remember, sine is the y coordinate. Okay, pi is over here. So sine of pi is 0. And then natural log of 1 is 0. So I get 0 over 0 there. So what I'm going to do is I'm going to say that this is equal to, by L'Hopital's rule. Okay, so you draw an L or an H here. I'll draw an L, I guess, for L'Hopital. A lot of books use H, but I've always used L. I don't know why. T goes to 1. What I'm going to do is I'm going to do L'Hopital's rule on any of these that have a problem. So the derivative of the top here is 2t minus 1, and the derivative of the bottom is 1. And then over here, I don't need to do L'Hopital's rule. And then over here, I'm going to do L'Hopital's rule again. So the derivative of the top is cosine pi t, right? But then the derivative of the inside, which is just pi. And then over the derivative of the bottom, derivative of natural log of t is 1 over t. So now let's plug in 1 and let's see what we get. So 1 here, I get 2 minus 1. That's going to be 1 on top. 1 over 1 is 1. So I get the vector 1. We already said this would be 9. Square root of 9 is 3. And then over here, cosine of pi, right? Cosine, I plug in 1 there. Cosine of pi is negative 1. And then times pi. So I get negative pi over 1, which is 1. So that's just negative pi. So the limit is a vector. Just be careful because the limit's a vector. It's not a number, right? All right, so that's 4. Let's look at 5. Oh, I'm supposed to just be doing odds. Oops. Okay, let's look at 5. Sketch the curve with the given vector equation. Indicate with an arrow the direction in which t increases. So r of t equals sine t phi t. R of t equals sine t t. All right. So this is two-dimensional. So let's make a t table. This is t. Over here is going to be sine t, t. So if I plug in, let's start with 0. I'll put 0 here in the middle. 0. Sine of 0 is 0, and then 0. So when the clock starts, I'm the 0 vector. Let's go, what do we want to use? I want to use a nice value so I can plug it into sine. How about pi over 4? So sine of pi over 4 is going to be root 2 over 2, and then pi over 4. Okay, so what I'll do is I'll get my calculator out here just to make sure I get these as accurate as possible. So root 2 over 2 is the vector 0.707, close enough. And then pi over 2, 1.57. I'm probably going close to off the screen there. So let's say that this is 1. This is 1. This is 2. This is 2. Then I'm at 0.7, so 0.707, then up 1.57, so somewhere around here. So a vector that goes from here to here. So I've gone from the origin vector up to that vector. And now I could do something like pi over 2. Sine of pi over 2 is 1. And then, oh wait, hold on, this was pi over 4, oops. Oops. This should have been 0.78. Okay, let me bring this back. 0.707, 0.7, so something right around there. And then pi over 2, I forgot, 1.57. So I go out 1.57 is up here, somewhere around here. So now I'm at this vector. And then let's do 3 pi over 4. So sine of 3 pi over 4 is still root 2 over 2. And 3 pi over 4 2.35, something like that. So I'm at root 2 over 2, which is 0.707. So it's here, but now I'm up 2.3, so I'm about right here now. Okay, and then I keep going. Let me go to pi. So if I'm at pi, sine of pi is going to be 0, and then pi is 3.14 approximately. So now I'm at 0 and then 3.14. So here's 3, here's 4, so 3.14, I'm about right there. So it's a vector goes straight up to here. And then what's going to happen is I'm going to start to go negative. All right? Start to go negative. My y coordinate's going to keep on getting bigger, right? And my x coordinate, or x component of the vector, is going to be following a sine curve. So remember, sine curves, you know, the traditional sine curve is positive, then negative, then positive, then negative. So my x value, my x component, is going to be positive, then negative, then positive, then negative. So what's happening here is we're basically drawing out almost like a sine curve, but vertically. And then it comes back the other way also, like this. So that's it. All right, let's look at number 7, which is, looks like it's 3-dimensional. T2 minus T2T. All right. Oh, by the way, on the last problem we did, it looked like this. As t increased, right, as t got bigger, the direction was this way. So when it draws this, it draws it like that, as t progresses from smaller to larger numbers. All right, so for this one, again, I can make a table. And let's start at 0 this time. 0, 2, 0, and then 1. It's going to be 1, 1, 2, and then 2, sorry. 2 would be 2, 0, 4. 3 would be 3, negative 1, 6. And then I can keep going. So what's happening here is that the x component is just growing, you know, by 1 each time. The y component is growing by 1 each time, but it starts at 2. And then the z component is doubling every time. So how in the world do we draw that? It's going to be tricky. Okay, 0, 2, 0 would be here. So we have a vector going from here to here. And then 1, 1, 2 would be 1, 1, 2 up here. So from the origin up to there. And then 2, 0, 4. So 2, 0, 4 would be straight up here like this. And 3, negative 1, which would be back, up 6, be there. So that's going to be really difficult to draw. But the important thing is that it's linear. Okay, so these are connected. So it goes like this. It's a straight line. Okay. And as time goes on, we are actually going in this direction. Okay. Number 9. Well, number 9's kind of worth drawing. Yeah, let's look at number 9. So for number 9, we have 1 cosine t, 2 sine t. 1 cosine t, 2 sine t. So if I make a table, t, I'm just going to put r of t here this time. If t is 0, I get the vector 1, cosine of 0 is 1, sine of 0 is 0, so I'm there. If I plug in, what do we want? Let's do pi over 4. I get pi over 4, I'm sorry, 1, that never changes. Cosine of pi over 4 is root 2 over 2, root 2 over 2 here, but then times 2, so that's just root 2. And then pi over 2, we get 1 again. Cosine of pi over 2 is 1, 0. And sine of pi over 2 is 1, but then times 2. So what we should recognize here is that cosine t, sine t, without the 2, that would draw a circle. If I make that a 2, what it does is it draws an ellipse. Now it's drawing an ellipse in the yz plane, and our x-coordinate's always going to be 1. So here's x, here's y. So my y-coordinate's always 1. So let's say this is 1. And then, let me draw a couple of these points. 1, 1, 0, which would be about here. And then 1, root 2 over 2, and up root 2, something like that. And then 1, 0, 2 would be up here. So this is what it's drawn so far, right? And it's going in this direction. And if I continue, this. What it's going to do is it's going to draw this ellipse, okay? But the ellipse is on the YZ plane. It's been moved out 1. It just keeps drawing the ellipse over and over and over and over. All right, that's through 11. Or no, I'm going to leave 11 to you. Now 11's harder to draw. I will admit that. But I'll let you mess with it. All right. All right, so now what? 11. So for 17 through 22, you're supposed to match. Let me just do one of these. 17. So let me try and match up the picture. What is x equals t cosine t, y equals t, z equals t sine t. This is also this. There we go. So what's happening here when we draw this? Well, notice the cosine t sine t, if that's all we had for these, then it would just draw a circle in the xz plane. But the fact that in front of these I have a t means that the radius, right, that's the radius in front of the cosine and the sine, the radius is actually getting bigger also as time gets bigger. So what we should have is, if we looked at just the xz plane, we looked at it from just the side, then what it should be drawing is a circle, but the radius should start small and get bigger. So it should be, a circle like this. It's trying to draw a circle, but the radius keeps getting bigger. And then what's happening is in the y direction, the y value just gets bigger. T gets bigger, the y value gets bigger. So imagine that as you're drawing this, the y axis is actually going away from us because of the right-hand rule. But imagine that you start in the middle, and your y coordinate your y component would be 0. And then as you start to draw this, let's say here's the plane, you start to draw this, but your y starts to get bigger, so you're going into the page like this as you're drawing it. So I think that looks like 2 on here, on your options. Option 2 looks like this. Option 2 looks like this. Sit like that. Okay? All right, so you can mess with the rest through 22. 23. Is interesting. Show that the curve with the parametric, they give you parametric equations, but I'm going to convert it. T cosine t, that looks like what we just looked at. T sine t and t show that this lies on the cone z squared equals x squared plus y squared. All right, so this right here, remember, this would draw a circle in the xy plane with an increasing radius. So that's going to be that spiral looking thing in the xy plane. But then our z coordinate's getting bigger and bigger and bigger. So it looks something like, in three-dimensional space. In the xy plane, which is the ground, is trying to draw the circle, but the z is getting bigger, so something like that. What we're trying to show is that it lies on this cone. Remember, this is a cone equation, and since z is isolated, the cone opens up in the z direction. So imagine a cone that looks like this. What we're trying to show is that that curve, that parametric curve, is actually on the surface of that cone. Well, this is pretty easy to check actually, because all we have to do is show that every point on here, right, every point, if we convert these vectors to points, if every point here, every x, every y, every z that comes from that vector equation lies on this cone, we're done. So they must satisfy this equation. So all I have to do is replace z with t. So t squared equals x, which is t cosine t squared, plus y, which was t sine t squared. And I just have to show that this is true, or figure out when it's true, like for what value of t is this true. So this is t squared equals, now I'm going to square this, t squared cosine squared t plus square this, t squared sine squared t. These both have a t squared, so factor out a t squared, left with cosine squared t plus sine squared t. But this is equal to 1, so you get t squared equals t squared, which checks out. T squared equals t squared. That's for all t. That's true for all t, which means no matter what t I pick, I'm going to satisfy that equation, which means I'm going to live on that cone. And I say to sketch the curve. I say in the homework to skip it, but there's the sketch. All right, where am I? 25. Okay, so at what points does the curve r of t equals, again I'm going to the vector form, t, I don't see a j in here, so 0, and then 2t minus t squared, I don't need the parentheses. At what points does this curve intersect the paraboloid z equals x squared plus y squared? So this is the same sort of story. I want to know for what values of t will I be able to satisfy this equation. So let me just replace everything here. Z is this, so 2t minus t squared must equal x squared, which is t squared plus y squared, but y is 0. So that's it. That's all you have to do is solve this equation. 2t equals t squared. I moved that one over. I'm moving both over, actually. Don't ever divide by t right now. That's a big mistake. I get t squared minus 2t equals 0. Do a GCF, factor out a t. And we get t equals 0, t equals 2. So at t equals 0 and at t equals 2, I should live on this thing. So let's just try it. Let's just check it. If t is 0, what's r of 0? So that would be 0, 0, 0. Does that satisfy this equation if I plug in 0, 0, 0? Yes. So what about at 2? Well, at 2, I'm at 2, 0, let's see, 2 times 2, that's 0 again. So, is that right? Hold on, 2 minus 2 squares, 4, 0. 2, 0, this doesn't look right. What did I do? Z equals x squared plus y squared. No, that doesn't look right. It doesn't look like it works at 2. So we have one extraneous solution here. Let me just double check everything. I think I did everything right there. Where's this? 25? Oh, I know what I did. Rough. Having one of those days. I was doing pretty good. I moved this over. This should have been 2t squared. So then this was 2t squared, and I pull out a 2t, and then this is a 1, and then this is a 1. Okay, sorry, basic algebra. I was thinking about this while I was doing this problem. I was like, hey, I think I might show my algebra class this, just to show them like this is part of a bigger problem. I can show them in class like how we would need to be able to do this problem. And then I sit here and I screw it up. Good job. All right, let's try 1. Okay, if we plug in 1, what do we get? 1 here, 0, and if I plug in 1 here, I should get a 1 there. And then check this into this equation, it should work, and it does. So, okay, Robert. 25, so let's see, 28. Find the vector function that represents the curve of intersection of the two surfaces. Oh, I like these problems. 28. See if I can do this one without screwing up the algebra. So 28. Find the vector function that represents the curve of intersection of the two surfaces. So I have a cylinder which is given to me to be x squared plus y squared equals 4. And I'm given a surface z equals xy. Now, they're not asking me to graph any of this, all right, but I'm going to try, kind of, to do this three-dimensionally. So let's see. So this right here, this is the equation of a circle, right, in two-dimensional space. It'd be a circle on the xy plane, which would be just on the ground. Have it a radius of 2. So if I go in each direction 2, right, then I draw a circle there on the ground like this. But the z value, right, the z variable is free, so my z can be anything. So I draw this cylinder like this. All right, there's my cylinder, right? And now I have another surface, which I'll do in a different color, which is this right here. So what I think what I'll do there is I will graph, try and graph this. It's going to be at the origin. Yeah, I know that's true. What happens if x is 0 here? If x is 0, then it doesn't matter what y is, right? Y can be anything. Y is free. But then z would be 0. So imagine that the x-coordinate is 0, the y-coordinate can be anything you want, right? But the z must be 0. It's going to basically draw a line like this. So far. Now I could have done the same thing. I could have let y be 0, then x would be free, and z would still be 0. So that would draw me a line in this direction. All right. Now let's try and do something here. This is going to be kind of tricky. Let's let x be a positive number, and let's let y be a positive number. So that would put me on the x-axis positive, the y-axis positive. So pick some point somewhere in here on the flat sheet of paper. It would be like the first quadrant on the flat sheet of paper. Remember, this is x and y. If I let that happen, then what happens? I multiply these two positive numbers together, I get a positive z value. So I'm going to be somewhere up, which is in the what? Remember the octants, right? 1, 2, 3, 4. The bottom is 5, 6, 7, 8. So this would be in the first octant. You would have this sheet coming up. It's really going to be hard to draw on here. Maybe from here it goes up and goes back to the origin. Just imagine kind of like this sheet up here. And it's getting bigger as I go out. The bigger that the x and the y get, the bigger, higher up it gets. Now, so I'm going to put here, you would be an octant 1 if that happened. Now, what if x is positive, but y is negative? So that would put you, x is positive, but y is negative, which would be over there. So what would happen there? Well, over there you get a negative number, right? Multiplying positive and negative. So now your sheet over here would go down. So it would go down over here. And you could do this. You'd be in octant. What octant would that be? 1, 2, 3, 4, 5, 6, 7, 8. You would be in octant 8. I'll just put 8. Octant 1. All right, you can do this, but you get this kind of idea that this sheet of paper, it does, or not a sheet, like a sheet on a bed, right, floating around in space here. And you've got, it does touch the axes, the x-axis and y-axis, it touches. But over here, it goes up, over there it goes down, and then you can check the other back. But what we're trying to find here is where the cylinder and the sheet hit each other. Whoa, find the vector function that would draw the intersection of those. And that seems like a really tough problem, but it turns out that it's not. Here's how we're going to do it. First, what I'm going to do is I'm going to try and draw the cylinder. Okay, so let's talk about the cylinder. I can do this. 2 cosine t, 2 sine t. That would draw me a circle in the xy plane. The thing is, right, that would draw me a circle this way. Remember on the cylinder though, the z was free. It could go up and down. So wherever these two hit each other, any point that these two intersect, definitely the point has to be on this, right? For sure. So this, if I draw this vector function so far, this should contain some of the points. Right now it would be, here's the origin. This would draw right now just that circle. So definitely all these points along the circle are on that cylinder. Now do they match, do they hit this? We don't know yet. So what about this last component? This over. The last component for this cylinder, it's free. So how do I say free? Well, I can't. That's why I can't use this to draw the cylinder, because this will draw a curve, not a whole surface. But in order to live on the surface, you must satisfy this equation. So that means your z value must be equal to your x value times your y value. So my z value here must be equal to my x value times my y value. So it should be this times this, 4 cosine t sine t. Just multiply those two together. If we sketch this, it should be the intersection of those two surfaces. All right, what's next? 29. I'm going to leave 29 to you. And then 39 through 63. Holy moly. Is that supposed to be 63? Yes, it is. Okay, I think this is a good time to stop for now.